All right. Sorry. I'm going to find some blank pieces of paper. I don't know. Figure it out. Get it to work. So yeah, we'll go on. Let's see here. The homework number 6, the last homework for the semester, is posted. Solutions for homework 5 have been posted. Homework 5 has not been graded yet. It should be graded by Monday. What else? Kind of recording videos for next week. Should get those posted before the weekend. We'll kind of see how next week goes. We might have some shorter days, just depending on things. So, but yeah. But basically, I mean, so the homework, if you've looked at it already, you'll see there's nothing on like statistical thermodynamics and stuff like that. So the material we're kind of covering next week. Basically, what like there we'll do some example problems. If it appears anywhere, it would appear on kind of the last regular exam, and I'll talk specifically about the type of examples that we'd be going over that could appear. Okay, so yeah, there's a couple of different topics and different subpoints from the statistical thermodynamics lectures that we'll go over, but some I'm going to try to emphasize more because they're more relevant for next semester than others. So, so yeah, any kind of questions about anything before we get going? I believe I already posted participation questions. Nod, yes. Hopefully I don't have any mistakes this time around. Statistically speaking, likely there is some, but you know, hopefully not. So, okay. Little questions here. Let's get started talking about electrochemistry some more, right? So last time we just mainly kind of talked about, right, reviewing the ideas and concepts of electrochemistry, right? Redox reaction, oxidation, half reactions, reduction half reactions, galvanic cells, your cell potential, standard hydrogen electrode, all those wonderful things, right? That hopefully you'd seen before, but we'll just kind of refresh our memories on them, right? And the Nernst equation is also something that you've hopefully seen before as well. Okay, but before we get there, we'll just kind of mind ourselves, okay, that the free energy is related with the cell potential, also referred to as the electromotive force, EMF. Okay, so you see electromotive force, EMF. That's the same thing as the cell potential, right? Okay, and here, yeah, okay. I was just trying to see how much. I think I kept most of the derivation already in these slides, but so let's go over briefly. I talk about it as well in the videos on this online, so don't want to spend too much time. But basically, the idea, right, is that the free energy change for your reaction, right, is related to some change in free energy with respect to the change in the extent of the reaction. We talked about that. We talked about equilibrium, right? That the change in free energy of a reaction is related with how the free energy changes with respect to how far the reaction has been progressing, right? Okay. And right, and so assuming constant temperature pressure, right, that this, just rewriting this, right, dg d zeta here, right, is dg equals delta g of the reaction times d zeta, right? And then recall, right, that our maximum work that can be done for non-expansion work, right, is related with the change in free energy, right, dg, right? So dg is dw max, where E here stands for extra, right, non-expansion work, extra kind of work, okay? And that's what we're talking about for electrochemical reactions, right? We're talking about a work related with transferring a charge across the potential, right? So right, the most common form of work that we think of is right, force over a distance, right? Pushing, say, an object up a hill, right? You push against a force. You have to apply some force over some distance. That's doing some amount of work, right? So transferring an electron is a very similar thing. If an electron transfers from one location to another over some distance, right? And while it's transferring from one spot to another, there is a potential, right, which is a force that acts on the electron, on the charge of the electron, right? Right. If it's transferring across the potential, that is the type of force that interacts with the electron, right? It's a Coulomb interaction, right? The potential, right, is related with some sort of kind of electric field, some Coulombic interaction, right? And so there's some force that's being applied to your electron as it's moving across that potential until you get some amount of work out, right? And so all we need to really do to relate this, this maximum amount of work done with the delta G of the reaction, things like that, is calculate what is sort of the work done with respect to some change in extent of reaction, right? For however many moles of reactants have transferred, right? How much work can I potentially get out? What is the maximum amount of work that I can get out for the number of moles of atoms and molecules that are being transferred, right? And so, right, using the fact that V is the number of electrons that's transferred, right, for some number of moles that's being transferred, right, then the total number of electrons transferred is just the extent of the reaction times the stoichiometric coefficient for the electrons, V, right? And then using the fact that Faraday's constant is the charge per moles, right? The total charge transfer is just the stoichiometric coefficient for the electrons times Faraday's constant times the extent of the reaction. There's a minus sign here for the fact that the charge of the electrons is negative. Okay. And so then that maximum amount of electrical work, right, is just the total charge that's transferred times the maximum potential that it can be moving against, which maximum potential is your electromotive force, your cell potential of your reaction, right? And then that charge is just minus VF, right? And so comparing, right, the change in the maximum work, right, with delta G of the reaction times the extent of the reaction, right, comparing that with this equation here, right, you see that the delta G of the reaction is just minus VFE. Okay? And all the units work out here because this is in volts. Faraday's constant is coulombs per mole, right? And the fact that 1 coulomb volt is equal to 1 joule. Okay? So the units of all this works out fine. So any questions about this, about where it comes from? How you get this relationship? No. It's just kind of fairly straightforward application of physics and the definition of work and work for a charge and things like that, right? Electrical work is charge times potential, right? How much charge did you move across that potential? That's your electrical work. So we just had to figure out how much charge we're transferring for some number of moles of reactants being reacted, right? Okay. And so this negative sign, right, means that when delta G is less than 0, the cell potential is greater than 0, right? And you have some spontaneous reaction, right? When delta G equals 0, the cell potential is equal to 0, and you're at equilibrium. And when delta G is greater than 0, cell potential is less than 0, right? And that's a non-spontaneous reaction in the forward direction, right? But with spontaneous in the reverse, right? And so this is why, like last time, I mentioned a number of times, right, that a galvanic cell is a spontaneous cell with a positive cell potential, right? Positive cell potential means you have a negative free energy change, so that is a spontaneous reaction. Any questions about this stuff? And hopefully a lot of this is kind of review, right? Right. So let's calculate the electromotive force or the cell potential of a cell whose Gibbs energy change for the reaction is 123 kilojoules. The stoichiometric coefficient for the number of electrons being transferred is 2, and F here is just Faraday's constant. All right. You have the number?
Negative 0.637.
Yeah. Right. So the cell potential is negative 0.637, right? You know it has to be negative because delta G is positive. And then to get this cell potential right, you take the 123 kilojoules, times that by 1,000 to convert it to joules, then divide it by 2, and then divide it by Faraday's constant. And that will give you the cell potential rate just using this equation here, right? Fairly straightforward. Plug in delta G, right? The main thing is to make sure you convert delta G to joules and not leave it in kilojoules, right? Otherwise, you'd get like kilovolts, I guess, is your final unit, right? You'd get like 6.37 times 10 to the minus, would that be 4 or something like that, kilovolts or something. So just make sure you're converting to joules so your units kind of work out and your final answer is in volts.
So is it in volts or volts per mole?
I guess this one is going to be volts per mole. Because Gibbs free energy of the total reaction is given as just 123 kilojoules. So this would be
Volts times moles.
yeah, sorry, volts times mole. Yeah, no, I mean, no, the cell potential should just be in volts. It's not a extensive quantity, it's intensive quantity. So delta G should have been given in terms of kilojoules per mole. Otherwise, basically, if you have a problem like this, okay, if Gibbs free energy is just given in kilojoules, that should be just given in kilojoules, assuming a total so many moles have been transferred, right? And so right? V here should hopefully correspond to the total number of electrons transferred, right? So V is just the stoichiometric coefficient, right, in your balanced electrochemical reaction, right, or half reaction, okay? Then delta G should be kind of a kilojoules per mole type quantity, because V is unitless if it's just your stoichiometric coefficient. But if you're saying I've reacted a total of, 8 moles of reactants, right, then I can calculate based off the stoichiometric coefficients the total number of electrons being transferred, and then I would use, right, the total number of electrons being transferred here, right? But really delta G here should be a per mole quantity, because often we think of this as like, right, delta G of a reaction is a per mole quantity typically, right? What's the free energy change per mole of reactant or something? Okay? But yeah, so here the unit should be volts. This delta G should have been given in a like per mole quantity. But yeah, your cell potential should never be like a per molar quantity, because the cell potential itself is intensive. Okay. All right, so another question here. I have these reduction potentials. Okay. The question is what is the cell potential for the galvanic cell that converts Cu to Cu2+? A, B, C, or D? Anyone have any thoughts? Some B's. Okay. Right, so you have Cu plus going to Cu2 plus, right? This is obviously not a balanced chemical reaction or whatever, right? Okay. Right, you'd need some like counter ions or something like that thrown in here to have this kind of balance, right? Because the charges is not balanced on the two sides, right? But just kind of ignoring that, right? And it doesn't actually matter, right? Because multiplying this reaction by any sort of stoichiometric coefficients and things like that doesn't change the cell potential, right? Because the cell potential is an intensive quantity. But basically, right, I have Cu plus going to Cu this reduction potential, and then Cu2 plus going to Cu this reduction potential, right? The reaction, right, has Cu2 plus on the product side, okay, right? So the oxidation half reaction is Cu going to Cu2 plus. So I got to flip this top guy, and then which changes it to negative 0.34. Add these two guys together, you get a positive 0.193. Okay. Right, and I know it should be positive because I'm told this should be a galvanic cell. Okay, and a galvanic cell is a spontaneous electrochemical reaction which has a negative delta G and a positive cell potential. Okay, so I knew the cell potentials should have been either A or D, and then I knew one of these had to be flipped to be negative before adding them together, because these are both reductions, and one of these has to be changed to an oxidation reaction, and so D. What did these be? And assuming that math worked out properly, that 5.33 minus 3.4 is in fact 1.93. Questions? All right. given this half reaction, will the following reaction be spontaneous in the cell potential of that half reaction? Yes. Right, it will be, and you know that because the half reaction here is the reduction of Cu2 plus, which is what is occurring here. And the oxidation half reaction is your standard hydrogen electrode reaction, which has, by definition, a cell potential of 0. So the total cell potential here is just 0.34 volts for the overall reaction, and that's a positive number. So the reaction, yes, will be spontaneous because of a positive cell potential. Questions about that? All right. So, right, the Nernst equation, since we already kind of derived and showed this relationship for the free energy change, the fact that delta G for a reaction is equal to delta G naught, right? The free energy change of the reaction at standard conditions, 1 bar pressures, 1 molar concentration, things like that, plus RT times the natural log of Q, the reaction quotient, right? Kind of show where all this came from by looking at our chemical potentials and how our chemical potentials change with pressure and so on and so forth, right? And so basically then using that and then the relationship we just showed and derived between free energy and the cell potential, right? We can divide both sides of this equation up top by minus VFE, right? To get the Nernst equation, okay? That the cell potential of any reactions related with its standard cell potential, right? Which again is the cell potential with 1 bar pressures, 1 molar concentrations, right? Minus RT divided by VF. Okay, those are all, right? R is a constant, V and F is a constant, right? Ideal gas constant and Faraday's constant. T is your temperature. V is the stoichiometric coefficient of electrons being transferred. And then ln of Q, right, where Q again is your reaction quotient. Okay. Right. Right. So this is how you can figure out what the cell potential is under non-standard conditions, right? And if you measure the cell potential of some reaction under non-standard conditions, right, you could use this equation to calculate what is the standard cell potential for your reaction as well, right? Which is done all the time in labs, right? Because typically in lab, right, you're not doing things under standard conditions. You don't have exactly 1 molar concentrations, 1 atmospheric pressures of things, right? And so you're typically measuring your cell potential under non-standard conditions. And then if you want to report the standard cell potential for those to use later and things like that, you would then, right, use Faraday's, or the Nernst equation, sorry, the Nernst equation to calculate it. Questions about this equation? And hopefully it's a familiar equation, right? One you've seen before in Gen Chem. Yeah. Right, and again, I mean, this is the equation we have from before, right? That's nothing new. Right? The standard cell potential is the standard free energy change of the reaction, right? I guess moving the minus VF on the other side, right? But yeah, this is just that equation up above, just saying at standard conditions, right, that cell potential is equal to the free energy change, right? But again, that's true no matter what. Delta G is always equal to minus VFE, whether or not you're at standard states or non-standard states, right? So, all right. And then at 298 Kelvin, right, so roughly room temperature, okay, and converting this natural log to a log, you can get this other form of the Nernst equation, which is just, again, plugging from these constants. So again, cell potential equals standard cell potential minus 0.059156 volts divided by V, again, the number of electrons being transferred, right, the stoichiometric coefficient, right, for those number of electrons being transferred. And then instead of the natural log, you have log base 10 of Q. Okay? And this form is used a lot as well when doing things at room temperature. And this form is used essentially in your pH meters. Okay. And I forget if I have an example of this now, or we'll do an example later. Maybe you have an example in the homework. I forget. Right. But right, if I have some electrochemical reaction where one of the half reactions is your like standard hydrogen electrode or something like that, right? Your H2 going to H plus or H plus going to H2, right? Right. In your balanced redox reaction, right? That is right. Any chemical reaction is considered an equilibrium reaction, right? So in that redox reaction, that Q for the redox reaction includes the concentration of H plus ions, right? Okay. So again, the idea here is, right? Let's actually fix that first. Right. Say go back to this reaction here, right? So Cu2 plus. Right. So we have that, say, electrochemical reaction, right? Inverted. Right. And so, right, the Q for this reaction is going to be related with like H plus squared over H2 Cu2 plus, right? Something like that, right? And so the log of this Q be the log of H plus, put 2 out here, right? And then plus the log of H2 over, or sorry, 1, well, probably easier just to minus the log H2 times Cu2 plus. Okay. Right. And so in my self-potential thing, right, if I have this minus 0.059 or something like that over V, and then I have this times the log of H plus, right, minus the log of H2 times Cu2 plus, right, multiply this stuff through, right, and you'll have like the self-potential, and then you have plus 0.059 over V times the pH plus 0.059 over V. Again, that constant I could have remembered incorrectly. I don't know. I could go back to the slide to look, right? And then the log of whatever, right? Doesn't really matter, right? But the main point is, right, is that the cell potential is a function of the pH, right? And so so you can use electrochemical reaction, right, to determine the pH of your solution, right? If you can measure, right, if one of the reactions includes H plus somewhere, right? If your balanced electrochemical reaction includes H plus ions, screen, right? Your balanced electrochemical reaction includes H plus ions, right? With that H plus ion concentration is going to be included in that Q, which will then you can simplify down to having, pH, right, in part of the expression, right, for what the cell potential is, but the standard cell potential, right? And so then you can measure, right, what the current cell potential is, and assuming you know everything else, right, which you potentially do, right? If you want to create your own pH meter, right, you'd set up your kind of pH meter, your electrochemical reaction in such a way, okay, that you know what the concentrations are of other things that are involved in that reaction, okay, and the only unknown is, say, the H plus ion concentration, right? And so then I could calculate the H plus ion concentration in the solution, right? And that will then get you what the pH is, right? Or you'd calculate the cell potential, and then you can calculate the pH from that, okay? Right? And so that is how at least some pH meters work, right? Is by doing an electrochemical reaction, measuring the cell potential, and then doing the math to calculate the pH from that cell potential. right? Where it's essentially the other half of the electrochemical reaction is converting H plus to H2 gas, say in your solution, right? So it's using the H plus ions in your solution, right, to complete the cell, right, for the reaction. Questions about that? All right. So calculate the electromotive force of that reaction when the reduction reaction, right, or when the pH is 7, pressure H2 gas is 1 bar, okay? Given your temperature is 298.15 Kelvin, right, and your standard cell potential is 0.00 volts. Don't need to have, sorry, I'm just gonna, where's that problem? Right here. Right. And as a reminder, I'm just going to copy that over real quick. No reason to make you have to remember this. Okay. Right. Anyone have answer they'd like to share? Yes, it is in fact A. So first, before doing the math, just talk about right, conceptually what we should expect So, right, at standard conditions, 1 molar concentration, 1 bar of pressure for H2 gas, right? The self-potential is 0, right? Which is saying you're at equilibrium. I know we haven't talked about the relationship between self-potential and equilibrium constant, right? But we have talked about the relationship between the self-potential and free energy change, right? And if self-potential is 0, free energy change is 0. If your free energy change is 0, you're at equilibrium. Okay? It's an equilibrium state, equilibrium change rate. So this reaction is at equilibrium at pH of 0, right? 1 molar concentration of H plus and 1 bar pressure, right? You're at equilibrium. You've now changed your pH to 7, so you greatly reduce the concentration of H plus, right? So according to the Le principle, what direction should my reaction shift to if I reduce the concentration of H plus significantly? Yeah, I'll go to the reactants, right? Let's shift to the left, right? So it's going to want to form reactants, okay? Well, if this chemical reaction as written is wanting to form reactants, right, then it is not going to be spontaneously forming products. So the delta G should be greater than 0, and the self-potential should be less than 0, okay? So we know just conceptually that the self-potential for this half reaction under these conditions should be negative, right? So the only possible answers are A or E. And then, right, if you write out, right, and then if we share, right, if we write out, right, again, E is E naught minus 0.059 divided by, in this case, 2, right, times the log of Q, which is the concentration of H2 divided by concentration. Oh, nope. So the answer is none of the above. I forgot that. Right, concentration H plus squared, right? And so this cell is equal to the standard cell potential minus 0.059 divided by 2. That 2 here is from V. I'm going to pull out the, right, this H plus is just equal to 1, right? And so I'm going to pull out the 2, okay? And this is going to be negative 2 times the log of H plus, right? Which is just equal to minus 2 times, or not minus 2, but plus 2 times the pH. So 2 times the pH times negative 0.059 divided by 2, right? And then the standard cell potential is 0, okay? And so those 2's cancel, and so you're just left, and the pH is 7, right? So you get 7 times 0.059, blah, 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 blah. So actually, as I did the math now in my head quickly, without working out in detail, it should be negative 4.14. Okay, so it should be a negative of C, right? No, it should be still negative.
Shouldn't it be positive because you just times negative?
No, because if you're going to use the pH, so I'll go back to this, right? So this negative doesn't cancel with that because I used a negative log is equal to my pH. So I got to use this negative to plug in for the pH, right? And so then I can just do a positive 7 pH, right, times this other stuff, and so that minus sticks around. Yeah. So, yeah. Right, if you want, you can cancel out the negatives. You just then need to take the log of 1 times 10 to the minus 7, which will give you a negative 7. And so then you'll still get the same answer. And I think there's someone on Zoom that had a question.
Oh, no, I think I said something, but I didn't see you got rid of the negative for the log of H plus.
Yeah. So I got rid of the negative in front of the log of H plus in order to use the pH, since the pH is defined as the negative log, right? Yep. So yeah. So any other questions? About this? Right. So the answer is actually negative 0.414, which is none of these. Yeah, I forgot the two coefficients in this equilibrium, and I tried to do it quickly in my head. I just focused on H2 over H plus. But yeah, there is the factor of 2 here that will pump out. Okay. All right. And then finally, right, the relationship between the standard cell potential and the equilibrium constant, right, is just kind of related with the relationship between the free energy and the equilibrium constant, right, under standard conditions, right? It's just now we have a factor of like negative VF, okay? And so yeah, so the natural log of K is equal to a positive VF standard cell potential divided by RT, okay? Right, if we recall from delta G, right, the natural log of K, which is equal to negative delta G divided by RT, okay? So you just substitute in for negative delta G, positive VF E. Okay? Yeah. Any questions? Any of these equations, right? Any kind of relevant equations that we talked about? All right. So then what is the equilibrium constant for a redox reaction where the number of electrons being transferred is 2, right? And the standard cell potential is 0.1 volts at 298 Kelvin. You have a value for K.
2,450.
Yep. 2,413, right? You know, K should be greater than 1 because the cell potential is positive, right? Is the first thing. Okay. And yeah, and then it's just looking for all the constants and things like that, right? Fairly kind of straightforward problem. Right, you're just plugging into the highlighted equation here. All right, so which of the following four conditions, A, B, C, or D, is inconsistent with the other three for a reaction that's set up under standard conditions? A, the reaction is spontaneous.
I had a question real quick.
Say that again.
I had a question real quick. You said that you would know K is going to be positive because that the EMF is positive.
Greater than 1, not positive. Greater than 1.
Oh, okay. You said greater than 1. Okay.
Yeah. If I said positive, that was incorrect by me.
I might have.
Greater.
Okay. Thank you.
Yep. Yeah. K can't ever be negative, right? K is always a positive number, but if K is less than 1, then that's telling you delta G for your reaction is positive, and then the cell potential is negative. Okay, because the K less than 1 means you're favoring reactants. Okay, which means you're not spontaneously forming products, and so on and so forth. Okay. All right. So again, right, which of these is not like the other, right? The reaction is spontaneous, delta G is less than 0, K is less than 1, E is greater than 0, or all four of these things are mutually consistent with each other. C, right? As you're just saying, right, K less than 1, right? K less than 1 is meaning you're favoring reactants, okay, not products, but the reaction being spontaneous, delta G being less than 0, the cell potential being greater than 0, all is applying. Products are favored, right? You're going to be forming lots of products spontaneously under standard conditions, so K has got to be greater than 1. Questions about this? And things like this are good sanity check, right? When working on problems, right? To just say, does my answer at least qualitatively agree with what I should expect to get based off of whatever information, right? Should I expect to get a positive delta G or a positive cell potential or a K less than 1, right? What things should I expect for my answer when calculating them? All right. So in this example at 298 Kelvin, right, we have two different reduction potentials, right? And the question is right, if they're combined to form a spontaneous reaction, right? Will A, zinc reduce Cu2 plus to Cu? Will copper reduce Zn2 plus to Zn? Will neither of these two occur in a spontaneous reaction, or will both of these occur in a spontaneous reaction? So do you think A, B, C, or D? A, right? Can't be C or D because one thing's got to be oxidized, right? And both A and B are reductions of some B or neither. Okay, because zinc can't reduce Cu2 plus while Cu is also reducing zinc 2 plus, right? That doesn't really make sense, right? And so basically, right, A is stating, right, that you flip the top reaction, zinc going to Zn2 plus, right? It's being oxidized, which causes Cu2 plus being reduced, okay? Which gives you an overall positive cell potential, will be a spontaneous reaction to the positive cell potential. So yeah, zinc solid will reduce Cu2 plus. and zinc solid itself will become oxidized. All right. So let's talk about a little bit more an involved question here, right? So I have the following electrochemical cell shown there, okay? And for this system, Q and QH2 have equal activities, right? Equal concentrations at 298 Kelvin. Given the two different half reactions that make up this total reaction and their standard cell potentials. The question is what is the pH of the HCl solution with the fact that the cell potential of that reaction is 0.190 volts, right? Not the standard cell potential, but the measured cell potential, right? So this 0.19 is not E naught for the overall chemical reaction, right? It is E, okay, right? The cell potential, not the standard cell potential. Oh. All right. So let's talk about this problem. So apologize for all my lovely mistakes here, right? But first thing that we want to try to do is write out the overall electrochemical reaction, right? Because basically, right, we know in this problem, we know what the standard cell potential is, or we can calculate it. We're given the cell potential, right? We're going to need to find Q, right? Right here, I'm using the fact that V equals 2, right? We're going to need to find Q to solve for what we need, right, for the pH of the solution. Okay. And so, right, and to do that, we need to write the overall balance redox reaction. Okay. So as a reminder, oh, I can't just alt tab over because then those on Zoom won't see it. So let me swap back here. As a reminder, right, this line notation, right, I have the anode and then the cathode, right, which means the oxidation reaction is occurring on the left, the reduction reaction is occurring on the right. So I got to flip my bottom reaction here to make this be an oxidation reaction. And then I add these two reactions together to get the overall redox reaction. And so when I do that, okay, I'll get this lovely reaction of 2Hg liquid plus 2Cl minus plus Q plus 2H plus, forming Hg2Cl solid plus QH2. Okay, I tried to put the phases of everything here, right, so that we know that the quotient here, okay, since we were given activities in the problem, I'm using activities here. The quotient is the activity of QH2 divided by the activity of Q times the activity of Cl minus squared times the activity of H plus squared, right? Right. Same thing as just the concentration, just writing activities, right? And then the cell potential is the cell potential of the reduction reaction, which is 0.6994, plus the cell potential of the oxidation reaction, which was the flip of the 0.2676 cell potential, right? To give us a total standard cell potential of 0.4318. So E cell standard is 0.4318, and E cell itself is 0.190 volts, right? And then I'm given Q, right? So questions about kind of what I have written here so far, right? Right, so what am I trying to find in the problem? What's being asked for? Right, I want to know the pH, right, which is the negative log, right, of the concentration of H plus. Or if you're using activities, right, you'd say the pH is equal to negative log of the activity of H plus, right? The effective concentration, right? Yeah. Right. So that's what we're looking for, right? We're trying to find the pH rate, which is essentially saying we're trying to find the activity of H plus, okay? And again, I have that relationship in this Nernst equation up above, right? When I have the cell potential and the standard cell potential already here, so I just got to kind of plug in for Q, right? Well, already we're given in the problem, right, that the activity of Q and the activity of QH2 are equal, right? So that means Q simplifies down to just 1 over the activity of Cl minus squared times the activity of H plus squared, right? But then to simplify things more, right, I got to figure out, well, what the heck is this activity of Cl minus, right? Well, if you go back to the original kind of the problem, right, that's notation, right, we see here in this problem, right, the H plus ions and Cl minus ions, right, are being added in through the addition of HCl, your strong acid HCl, right? And so what that means, okay, is the fact that, right, so HCl is what is contributing to the Cl minus concentration and H plus concentration, right? Which means that the concentrations of both of these things, right, H plus, Cl minus, are going to equal in solution, okay? And then furthermore, right, since they're coming from the same salt, right, the same ionic compound, right, the mean activity coefficient, right, that gamma plus or minus, right, is the same for Cl minus and H plus, right? Those are the same, which means, right, the activities, which is just the concentration times the mean activity coefficient, right, is the same. So the activity of Cl minus equals the activity of H plus, okay? In this problem, right, those activities have to be equal, okay? Right, because the Cl minus and H plus that's being introduced on the reactant side, right, is just coming from that HCl, right? There's no other place where H plus and Cl minus are being introduced to this solution, to this reaction. So their activities are the same. So Q here just simplifies down to 1 over the activity of H plus to the 4th. Okay. So questions about that? And so going back to the Nernst equation that you can't really see, right? E equals E naught plus 0.059156 over 2 times the log of 1 over a H plus to the 4th. Okay. Simplify this down just a little bit. Should there be a plus here, or am I messing up? That should be minus. I feel like I'm messing up. Let me just go back real quick. Right, the Nernst equation should be a minus. Yeah, that should be a minus. I don't know why I put plus. Okay. This should be a minus sign. Apologize about that. That's minus. Okay. Up here, that was also minus. Okay. So this is minus that. Okay. Now, again, using the fact that the pH is related to the negative log of H plus, okay, the log, right, the log of 1 over AH plus to the 4th is equal to negative log times 4, okay, of activity of H plus. Okay. So the log of 1 over activity of H plus to the 4th is just going to equal 4 times the pH. Okay. All right. So this again, you pull out the 4, the exponent, pull it out, that gives you a 4, and then 1 over x, log of 1 over x is just negative log of x. So you get negative 4 times the negative log of H plus, or the activity of H plus, which gives you just 4 times the pH. So plugging that back into here, right, you get the cell potential is equal to the standard cell potential minus 0.059156 divided by 2 times 4 times the pH. And then plugging in for the cell potential that's measured and the standard cell potential up here, right, you have 0.19 equals 0.4318 minus 2 times 0.059156 times the pH, right? And so now I just have this simple equation here that I can use to solve for the pH. So when you do that, okay, you will get a final pH here of 2.04.
You do it differently because the Nernst equation is the natural log of Q, not the log of Q, so you have to convert it. Like you go back to slide.
Yeah. So on the slide here,
You got 4 times the pH, but it's different. You have to convert a log.
well, that's so in this problem. So how I did the problem is I used the minus RT divided by VF. I should have used the fact that at 298 Kelvin, that this converts, like if you convert this to log and plug in temperature 298 Kelvin, you'll get that 0.05. You'll get this equation here. Yeah. So this is true at 298 Kelvin. So in the solutions on the slides, for those who are looking up, right, I use the general Nernst equation and use the natural log and try to convert natural log to log and things like that. But here I use this, but in my workout here, just skip that step. I already used the version of the Nernst equation, which assumes 298 Kelvin and uses the log. So yeah, but here, right, I use the Nernst equation itself, okay, right? Then convert the natural log to log, okay? To get the natural log of Q is just 9.21 times the pH, and then use that to get this exact same equation, right? So that 2 times 0.059156 should hopefully come out to be 0.1182. And so then you get the exact same equation, you get the pH 2.0. So yeah, so how I did it online or on the slides here versus how I just worked it out in person, right? It's slightly different, but both should give the exact same. So any questions about this example? Okay. All right, mainly in this example, you want to make sure that you take the effort, right, to write out what is the balanced redox reaction, right, for the cell, okay? And then the biggest kind of trick is just identifying the fact that, right, the activities of H plus and Cl minus have to equal each other, okay? Because of the fact that the concentration of H plus and Cl minus in this problem, right, come from the addition of HCl into the solution, right? They come from the same salt, the same source, right? Now, if I added like, you know, HI and NaCl, right, in different concentrations in the solution, then those wouldn't be equal, and I wouldn't be able to use kind of that simplification I did, and I need more information to solve the problem, right? But because H plus and Cl minus come from the exact same salt, right, or in this case, strong acid, right, strong electrolyte, you know, the concentrations are equal, and I can simplify things down to get pH 2.0. All right. So the last example problem here that we'll just kind of discuss real quick, right, is a kind of KSP type problem, right, where I can use electrochemistry to measure the solubility product constant for some insoluble salt, right? So let's consider the redox reaction given here, okay? It says the cell potential of 1.2 volts at 25 degrees Celsius, okay? Is that 298 Kelvin? Question is, what is the solubility product equilibrium constant? And then the solubility of AGI. All right. So again, I'm going to write out the line notation here so we can kind of see what is going on in overall chemical reaction and kind of figure out what the heck, right? So again, let's start this line notation to write out our redox reaction, right? So at here, I'm having the oxidation reaction, right? Anode, cathode. Right, at the anode of the oxidation reaction is AgI solid, right? Going to Ag solid plus I minus. Wait, no, that's the reduction reaction. Shoot, right? Yeah, this is Ag. Yeah. Sorry. Right. Right. So the oxidation reaction, right? Oxidation. Sorry, it is Ag solid plus I minus, right? Forming AgI solid plus an electron, right? And then my reduction reaction on the other side, okay, this is AgI aqueous, right? Plus an electron forming Ag solid plus I minus. Okay. Right. Which AgI aqueous, right, is just Ag plus I minus, right, aqueous plus E minus. Okay. Right, so my overall chemical reaction is the sum of these two things, right? Okay. But if you sum up these reactions, I'll even leave the AgI aqueous, right? It is, right, AgI aqueous forming AgI salt. Okay. So literally the net redox reaction for these coupled reduction oxidation reactions. Okay. Right. Which again, AgI aqueous is Ag plus I minus, right? Both aqueous. Okay. And so this, right, this is my net reaction, right, in this chemical cell, right? This electrochemical cell, that is my net reaction. Okay. Right? Which the K for this reaction, right, is just 1 over KSP, right, for AgI solid, right? Because this is just the flip of the KSP equilibrium constant, right, or the equilibrium reaction, right, the solubility product equilibrium reaction for the salt. Okay. Right. Okay. Right, and so again, right, if we're looking to get equilibrium constants or things like that, right, okay, we need to get self-potentials and such, right? And so again, we're given the, I think we're told the standard self-potential, is that right? Yeah, right. The self-potential of 1.2 volts, okay. Right. So this, right, has E cell of 1.2 volts, right? Okay. So if I wanted to flip the reaction, okay, so that I get my KSP, right? The flip of this reaction, okay, has, so AgI solid going to Ag plus Cl minus, okay. Right, that has an equilibrium constant KSP, which has a self-potential of minus 1.2 volts, okay. And so then, right, ln of KSP here, right, it's just equal to what, VF over RT times the self-potential, right, the standard self-potential. Okay. And so, right, that's 2 times Faraday's constant, what, 96485, I think, over 8.314. Temperature was 298 Kelvin. And then self-potential was minus 1.2. Oh, and the number of electron transferred is 1. Sorry, not 2. Right, V is 1 here, right? Going up to these reactions, right, it's just 1 electron being transferred. Okay. V is 1, right? And so you just got to plug everything in. That's natural log K. Take the exponential both sides, right? And you'll get the value of K, right? So just going back to the slides. And right, plugging in all that wonderful stuff, right? You'll get K, which is your KSP, 5.07 times 10 minus 21. Okay. That is the KSP for that salt. So questions about this problem? If you're not comfortable and familiar with that line notation that we talked briefly about last time, right? Just look over some of these examples, other examples, review the lecture slides, lecture videos, and things like that. Okay. So you're familiar, you're comfortable with what that is and how to convert from that to your redox reaction. Okay. All right. If there are no other questions, then that is it for today. And then I will see you guys on Monday. And I'm happy to stick around for any questions people might have, both on Zoom or in person.
I want a quick question.
Yeah. Yeah, because so for that reaction, right? So the question here is right here I had K equals KSP, right? For this reaction, I have the ions added together to form the solid. The equilibrium constant for that reaction is 1 over Ag plus times 1 over I minus, which is just 1 over the KSP, right? Because your KSP for your solid IgI, right, is this reaction here, which is the concentration of Ag plus times concentration Cl minus, right? So that's just like the KSP, yeah, the KSP is this equilibrium reaction specifically, right? So if you don't remember from Gen Chem, right, the solubility product equilibrium reactions are solid, forming aqueous ions in solution, right? So that's what that KSP is. Yep. I guess the problem asks what is the solubility, so you can essentially calculate that later using good old ice charts and one stuff. But, I don't think I had that in the slides. Pretty sure. Let's see. No,